To give one more example, suppose that this is what our distribution looks like. So we have a lot of, the highest probability seems to be that the outcome will be closer to 2. It's very unlikely that the outcome will be closer to 0. So this may be the lifespan of some particular part. So we'll just call this L. Okay, well, in this case, this is modeled by the function y equals x. So this is a triangle, and I'm going to use, some basic geometry. I know the area of a triangle is equal to 1/2 times the base times the height. So in this case, I can confirm that the area is still 1 underneath this by taking 1/2 times the base, which is 2, times the height, which is, oops, I guess I didn't list that, a density of 1. Remember, density is just a value that makes the area equal 1. So 1/2 times 2 times 1 is actually equal to 1. And therefore, this is a valid probability distribution. Similarly, if I wanted to find the probability of, let's just say, the outcome occurring between 1 and 2, well, number one, that area, that should be more than 50% right there. That should be fairly likely. Okay, so I want to know the probability that the lifespan is between 1 and 2. So the question is, how would I go about doing this? It's not quite rectangular, and it's not quite triangular. So here's what I'll do. I will think about this in two pieces. I'll split this up into a rectangle and a triangle, and then figure out the area of both of these. But the question is, how tall is my rectangle? So this is a value of an x value of 1, or a lifespan of 1, so y would equal 1 in that case, because y equals x. So this would be a height of sorry, this is not 1, this is 1/2 x, excuse me. So y would equal 0.5 times 1, which is 0.5. So this would be 1/2 right there. So that means that this rectangle is 1/2 tall, or the height is 1/2, and the base is 1 wide. So that means that the area of the rectangle would be 1 times 1/2, which is equal to 50%. So there we go. So it's already 50%, just that area there. That's 0.5. And then the area of this triangle here, well, this triangle is also half a unit tall, and it's 1 unit wide. The area of a triangle is 1/2 base, which is 1, times the height, which is 0.5, and half of a half is a quarter. So the sum of these two areas is 1/2 plus 1/4, to giving me a total area of 0.75. So there's a 75% chance that the lifespan would be between 1 and 2 units of time. The most common type of continuous distribution is called a normal distribution. The normal distribution is most commonly occurring in things like nature and in aggregation of data for very mysterious reasons, sort of like pi. It's a really, really beautiful thing. The area under this curve is also equal to 1. However, the probability density function, the equation that will give us this curve, is equal to this big gigantic mess, which you will need to memorize and use frequently. Just kidding. This is something that we're going to avoid using, but if you were to use an integral and you found the area under this curve, then the area under here would of course be 1. Unfortunately, the one thing about normal distribution is that it goes on infinitely in both directions. So it continues going that way and it continues going that way. But if you take the area from negative infinity, so the probability that x is between, I shouldn't put an equal sign there, is it less than infinity but greater than negative infinity, is equal to 1. So this guy's domain is really wide. Okay, so you can probably imagine this thing is symmetric. So, well, not the way I've drawn it, but if this is the center point, then this is actually our mean. Our mean is right in the center. Our standard deviation is denoted by sigma, and it'll be the same amount of space in one direction as in another. So this would be positive sigma, mu plus sigma. This would be mu minus sigma, the standard deviation. And then, of course, the area from here to here would be 50%, and the area from here to here would be 50%, giving us a total area of 1. Now, we're not going to be able to find these areas by hand. We can certainly approximate them, but we will use a calculator, we'll use technology in Excel to be able to find these areas in our next discussion.